So for the lab 4, we need to use the optimal receivers for our transmitted binary shift key signals. In the lab 3, we create the binary shift key signals with the noise. So this will be the transmitted signal, and in the lab 4, we will receive them, use the optimal receivers. And there are some tasks. We have 4 tasks we need to do solved, and we need to add optimal correlation result for the all program, which means we have 3 different modulation types, and we need to plot the receive the noise signal and integral signal, and the task 3 where we need to perform the detection and output the received data in the command line and compare the result to the original selected data vector, which means our uh, received signal after the optimal correlation receiver, and the data will be changed if we compare it with our initial the binary data, and we need to analyze the influence of the noise power, simulus ratio on the accuracy of the detection. So here we need to use a for loop, and for the each received symbol will process separately. So n will be the number of the binary symbol data, and in my case I have the n is the 10. So we will get each of them work for loop of the use the for loop function to calculate all of the type them symbols, and here we need to specify some index here, and it start from the first symbol and plus the next symbol, and we need to it controlled by the k. So k will start from 1 to the 10, and each of them has the each of samples has the specific index, and you already know the 200, which is in the lab 3. We already specified that 200 is the number of the carrier signal samples per symbol. So here, this is for the one symbol, and we have the k minus 1 symbol, and all of them will get the index in here. Then we use the multiplication, and here we use the dot multiplication operator, and this is the modulated. This is the first. This is the received noise signal. This will be yeah. This will be the correlator multiplication. So the SM and the SI1, we need to use the calculated continuous integral, and in this case we in the lecture part we use the multiplied with the carrier frequency, and we do the integral here. But here we need to use another function is the COMSUM function, which calculates the sum cumulative for each symbol. We don't want only show the last result. We need all of them to show, and we need to append the result to the integration signal, and all of them step by step. So let's first check how to use this one COMSUM function, and we just create it. Help COMSUM. And if we have this one, suppose we have the on to we use the console. Will be so first is 0, the second is 1, and the third will be the plus them together 3, and the fourth will be plus the first 4 symbols together will get 6, and the fifth symbol will be the plus the all fifths, the first fifth symbols together get 10. Then we keep go on that it meet our cumulated idea for the each symbols, and we need to append all of the symbols together. Next we can plot it. So let's do it together. We need to do this work based on the third practical work part, which, and for me I just keep going, and you can make the separate code or can you also can keep go on based on the third practical exercise code. So it will be the first practical work. And use some separate line. And will be the accelerator optimal. And for the, we need to firstly, in the task, we need to plot the received noise signal. So in order to separate with the first figure, we need to have a separate figure with the figure 2. And subplot to plot. So only shows we need to plot the noise signal. Copy it. And for the label will be the same. Binary signal with the noise. So this is the first. And we need to calculate the received each symbol. So we need to specify some bracket, and for the after the integral output signal, and we I one is the bracket and all of them will, after calculation, will append in this bracket. Now we use the for loop, and it starts with the k. N is the length of the binary data vector. Here, in my case, I have 10, so N is the 10. And we need to specify the index with start with the here. Last one will change. Will be the segment. The next one will be the operator multiplication. So we have 1, I will be S0 dot multiplication with the uh, binary signal with noise, and it should has the it should according our index. So it should follow our specific. Will be the correlator multiplication. And next we will is calculate the continuous the integral, and we need to use the console function and append them together to the append the result to the integration signal. And we start from the SI1 to the so the continuous integral. In the next we'll so it finished for the append the data, and we need to the draw some threshold value, and for bxk, and the threshold is the E divided by 2 E energy signal, which we already calculated from the noise power here, EB, energy of the bit. So if the after the continuous the integration signal greater than the threshold E divided by 2, then we can say it will be the 1 packet. Will be the K. And so it will be the detector symbols. With threshold. So for all of the symbols, and we need to plot the integral the signal. Integrated. And change the with and with the S I And we need to add some threshold line with 0, and it started with the 0 to the t end. Threshold will not change half energy, and we give it a red line. So here we just and this will be the first. And also we need to compare the data. So it will be the data for comparison. We just append uh, the binary data as B, and is the detected the symbols, which if it's correct, the both of them will be the same. So let's write. There no mistake. Oh, here I didn't change the here initially single noise ratio. So this is the non-single noise ratio here, and we can see here for the one symbol, and after the multiplication, and it will increase, and it can increase get to the threshold with half energy 9, and if it greater than the threshold, it will be the 1, and for this is for the 3, and this is for the 4. So the 3 and 4, both of them from the binary transmitted data, binary data is all the 1, and for the 5 and the 0 and 6, it's 1, and for the 7, 8, 9 will be the 9, 10 will be the 1, 1. So that is the idea, and we can see here just here, and we can see here this is after the threshold detectors symbols. This is our transmitted binary data. So for the initial case, it's 100 and it's quite good. And if we decrease the single noise ratio, it starts from the 30, how it will goes. And you will see for transmitted data, it still has some noise, and for the here for the operator receiver, we can see some noise at around close to here, but it increased very small, and basically cannot reach to the threshold, and for the one symbol, and it also can increase to the 100. So it's quite clear and quite good, and for the here, no errors happen. And for the, we still can decrease it as like 10. So you will see the transmitted data with lots of the noise, and for the people cannot recognize it. So how about the optimal crowd reader receiver? And you will see it's still good. For that, we don't have the, if there is a noise after the coloration receiver, and for the zero data, and it still cannot increase to the threshold. All of them can, maybe them can decrease or it can increase, but it cannot reach to the threshold. And I think there also will be the no errors happen. So we can decrease at like 3 what will goes, and here, and you will see some noise will be happen here. Where C, it should be the 1, and here we have some, here also this mistake. So, and you will see the second symbol, and for the last symbol, and here we have all there were 3 errors happened. So for you, I recommend you to try more different values to get the minimal single noise ratio can transmit the data with any mistake. And this is for the amplitude shift key, and for the frequency shift key, we just copy it and make some modification. And here. So frequency shift key, we need the frequency signal with the noise, and we need 2 brackets for the integral of the output signal, and this is 1, and we need 1 more. This is the 2, because we have 2 different frequency, and index will not change. And for the carrier symbol, we have the S1 and S2. Similarly, for the continuous integral process, we also have the S1 and S2. S1 and S2. So, and so if the S and the, we don't have the threshold here, we just compare the both of them. According to the lecture, we already know that frequency here, and the decision, if here is good, we can choose this part. If here is good, so in here in the code, we just compare both of them. Side 2 with no threshold. With both. with both integral signal. And for the here we have the and, also have the and. And we need to plot the both of them. So here we need to add one more here. Sorry. BFSK. And no, we don't need the threshold. So here, this part we'll just delete it. Second, correlator receiver. You see, we have the both correlator receiver. And for the output data, for the compression, that will be the here. So here with frequency, and everything seems correct. That's right. Yes. Just from the initial, come back to the initial noise ratio here and here. Well, here this found this mistake, I think. Yes, multiplication is incorrect. S1, S2 with the should again. So this is the transmitted signal with the noise, and we got this in the optimal receive part. We got the noise. The signal it has the two different frequency, and here. So if the uh, uh, first let me see, here we have the two different observatory, and so uh, here, yes, for the two optimeter we have the zero voltage. Just compare it with this part, and so here is the 0, and we can see here is also 0. And for the first correlator receiver will be the 0. And we will choose this part. And if this is 1, and we will choose this part. So the answer for the output data, so we can see here this will be the correct. And let's decrease the single noise ratio with 10, and we will go on. So basically, it still can see, and here will is quite good. Even it has very strong noise amplification, and we can see here noise will still can get the correct result. And for the lower single noise ratio, and here with here just here, and will some of them maybe calculate some noise here. Let's check the received symbol. Well, still no result. So it seems you can still decrease the single noise ratio to get the minimal requirement for the without any mistake. And this is for the frequency shift key. And here we need to calibrate the receiver and which one is good, which one or which of them meet with this regulation, then we will choose any of the one of them as the detector symbol. Then we compare with the transmitted binary data. Then we can get this. We can check any mistake whether it will happen. So let's move to the final frequency phase shift key, and I'll still just copy here, and so here in the here we need to change some we need to change some threshold, because in the lecture we know that we convert here. No, we convert yes, we convert the 1 to the -1, 0 to the +1. We convert to the NRZ. So here, for here, this will be the half of them, and here the threshold will be the half of the both of them will be the 0. So we have the new threshold, and let's do it. And for here, we change the index. The index not change from the and one to tolerate multiplication, and here and here. So we don't we here if we change here is 0, and here SK, and the threshold is not half of the energy, it's just 0, and yeah, and last one is the nothing more need to change, though we need to compare with that. So what we'll see, yeah, convert the single noise ratio, come back to the 100. There is some mistake, I think. 945. Yeah, here. PSK. So we have this one. And for the 0, we convert to the here you will see here, which will 1 to the -1, and for 0 to the +1, for the 1 convert to the +1 -1, and well, it seems there is some mistake here, and we can see here, check it. So it converted to the all of them opposite, which means our threshold we cannot change the greater than 0. It should be the less than. Then it should follow our non-return to 0 definition, which is the 1 convert to the -1, 0 convert to the +1. That's right again. So here, nothing to change here. For the plot, there is no mistake. And for here, we can see everything is correct here. And we just try to any lots of different synchronous ratio. And you can see lots of noise added in some. And so based on them, quite good. I think there is no mistake occurred. No mistake occurred. And for the 3, yeah. So even 3, also no mistake. No mistake. But I think it's close to the this close to the minimal single noise ratio without any mistake happened. So you can try more different values and find out which is the minimal single noise ratio, and you can compare with the 3 different modulation type, which and make your own conclusion, and how does the single noise power or single noise ratio influence on the detection accuracy. So that is all I want to share with you today. And thank you for your attention, and see you guys next week. Thank you.
Thank you.
Bye bye.